What does it take to change the world? Historically, change has usually been slow-moving and methodical, taking hundreds of years for even incremental advances to be seen. But over the past century, things have shifted, and that trend has reversed to the point where some forms of change now come at breakneck speed. Just look at our personal computing devices as an example. Our cell phones, laptops, tablets, and other devices come out to great fanfare one day, only to be labeled as obsolete and clunky after only a few months. In our consumer-driven world, that type of fast-moving change is okay. But when it comes to building large-scale, long-term items like cars, buildings, and aircraft, the process is slowed down to make sure those items are as safe and reliable as possible. This disciplined and deliberate process can be seen clearly in the aircraft industry. Before new technologies are implemented, they are first tested and retested for many years to make sure they will perform perfectly every time. And because getting it right is so important, the workload is often shared with thousands of highly skilled industry personnel, as well as with the brilliant engineers who run our national wind tunnels, labs, and flight facilities at NASA. Much of the early testing begins at NASA, where engineers bring the breadth of years of aeronautical knowledge to bear on each new design before a craft is ever placed into service. But how does this testing work, and what is the process that researchers go through to make flying as safe as possible? Coming up on this episode of NASA X, we follow members of the Environmentally Responsible Aviation Team as they conduct a variety of tests on new aircraft designs that are in the early stages of development. We will follow them to see how initial designs and ideas are moved through the pipeline from computer drawings and wind tunnel models all the way to scale model aircraft and full-scale flights. We will see how each new step is bringing us closer to flying on board future aircraft that are more efficient, quieter, and safe. And we will see how each new step is helping to change the way we all fly. By now, most people are familiar with the story of the first flight the Wright brothers took at Kitty Hawk in 1903. That 12-second flight, captured in this famous picture, was the first stepping stone to modern air travel as we know it today. What is often forgotten is just how much time, planning, study, and trial and error was performed by the Wright brothers to get to that first flight. For at least 10 years prior, the brothers went over all known text and information they could find that related to the problem of flight. They tested their theories with small-scale designs and with large-scale glider models. But around the fall of 1901, the brothers realized that much of the data they'd been using from others was faulty, and the only way they could get accurate data was to get it themselves. Shortly after this realization, they built a very simple wind tunnel that they could use to test their different ideas for the ideal wing shape. By 1902, the brothers had accumulated more information on the design and behavior of wings than anyone else previously in the history of this field of study. With this knowledge, they had the information necessary to design and build the world's first successful heavier-than-air flying machine. After all this hard work, the Wright Flyer lifted off from the sands of Kitty Hawk on December 17, 1903, and changed the world forever. Even though the world and the technology that we use every day has changed dramatically since 1903, aeronautical engineers still follow the same basic principles that the Wright brothers used to build aircraft today. They still build small test vehicles, assess them in wind tunnels, and often make flying scale models to further flight characteristics, and finally build a full-scale aircraft to continue the development. Obviously, much of the testing of today is accomplished by aircraft manufacturers, but many people don't realize that virtually every new aircraft design is still tested at different NASA centers around the country. This is because NASA is still the world leader in aeronautics and has the facilities and brainpower to continue to improve the science of flight for all of us.
When people decide that they're going to take a flight, what are they looking for? Are they looking at how long it's going to take me to make this flight? Not necessarily. They're looking at the number of stops and the cost. And so the work that we're doing directly impacts those. Fuel burn, emissions, noise. So for the general public, what we're doing is making it less costly for you to fly without any reduction in your safety, and we're doing that while we're making it better for the environment.
Today, one of the biggest areas of focus in the aircraft community is on environmental issues. There is a growing realization that if pollution of all types can be reduced, then costs and aggravation for the traveling public can be cut dramatically too.
Environmentally responsible aviation project is making a significant and important contribution to aviation, because it primarily is working on reducing fuel consumption and also reducing environmental impact, negative impact to the world from the aviation, namely emission and noise. So ERA is the centerpiece of our portfolio.
Here at NASA Langley in Hampton, Virginia, a small group of aeronautical researchers from the Environmentally Responsible Aviation Project are at the cutting edge of this research, attempting to take the next steps to make aircraft more efficient and less noisy. Their goal: to simultaneously reduce aircraft drag by 8%, weight by 10%, fuel consumption by 15%, emissions by 75%, and reduce overall aircraft noise by nearly 90%, all by the year 2025. These lofty goals are definitely attainable, but a lot of work and testing needs to be completed now to get us there. In today's world, testing new designs always begins on a computer screen. Complex computational fluid dynamics often helps researchers get a head start in understanding flight characteristics of new designs. But even with the most sophisticated computer renderings, at some point, actual hardware must be tested in wind tunnels. So after the computer models are run, engineers send exacting specifications to NASA's model makers, who build these small-scale aircraft for testing in wind tunnels. These models are used to help validate and answer numerous questions about new and existing aircraft designs, including how to help mitigate noise pollution, reduce fuel burn, improve flight characteristics, and so much more. Of course, the art of creating aircraft models is decades old, but one of the newest and most exciting technologies being used to predict and improve aircraft characteristics is located here in the 14 by 22 wind tunnel at NASA Langley. This new technology is a very sophisticated acoustic array that is helping to reshape our understanding of aircraft noise.
Well, the array is composed of almost 100 microphones. And what it does, it phases the signal such that it's able to go to a different location and and amplify the signal such that we can pick particular spots and be able to determine exactly where the noise is coming from by focusing on different locations. It's kind of taking a snapshot so that you'll be able to see it in a 3D. And you'd be able to, normally you would only measure a single microphone result, but now we can actually pinpoint it. We've done acoustic testing in this facility primarily for helicopter work, but never to this magnitude as far as the array, the towers that we have. But this is the most extensive in this big facility.
This new array is rapidly changing how aeronautical research is done. To better understand why this array is so valuable, we have to first look back at the aircraft from the 60s and 70s. During those days, the biggest cause of aircraft noise was the engines themselves. But over the past few decades, huge strides have been made to lessen the noise level of engines. So now the non-propulsive elements like the slats, flaps, and landing gear are on par with the engine noise. This array in the wind tunnel, in conjunction with the computational fluid dynamic models, has helped researchers predict how striking the change will be in the coming years, as seen in this simulation. This simulation has helped researchers understand that they can redesign elements of the non-propulsive parts of the plane with dramatic results.
We really have done a good job of designing these concepts using the virtual space, and they are performing as predicted, mostly as predicted. Typically, it takes 10 to 15 years from the time that you really create a technology that you have looked at all aspects of it, make sure that it doesn't have any negative impact. It takes about 15 to 20 years to get on a real aircraft. And so we have been working on this technology for the past few years, and we are part of a program with our partner Gulfstream, that once we are done with this experiment, that we down select some of our best performing noise reduction concept for both flap and landing gear, and pretty much put it on the Gulfstream aircraft, and we use that aircraft as a test bed to really find out the performance of these noise reduction technologies that we're working on in real environment, which is the actual full-scale aircraft. We're working on, for the flap, we have shown through our modeling and simulation that you can reduce it by about 60–70%. And for the landing gear, we have shown that maybe 50 to 60%. And so what we are trying to do here is through computational simulation that is really hold, and the technology that really produced that amount of noise reduction.
After the wind tunnel validation, the next step for some engineers is to test an aircraft's flight characteristics even further by building small-scale models that can be flown remotely in a real-world environment. Often the data they glean can be a game changer for these new designs. In California's high desert sits one of the most storied flight facilities in the world. Here on NASA Dryden's dry lake bed, many of the world's flight records have been broken time and time again. One of the latest flight records to fall came at the hands of the engineers who fly this aircraft, the X-48C. This unique hybrid wing body design is a departure from current aircraft designs, but has shown great promise in reducing both noise and emissions. For over 6 years, different versions of the X-48 flew more than 120 flights, far surpassing the record for most flights by unmanned X-planes. The X-48C began its life as a wind tunnel model. After that initial testing, it earned its wings and was converted to a flying scale model that flew the final 30 flights in the storied X-48 history. This final configuration of the X-48 is being flown to evaluate truly low noise capabilities.
So we've done wind tunnel testing, right? We did wind tunnel testing with both the B configuration and the C configuration. And the next step beyond wind tunnel testing is to take a smaller scale, this is an 8.5% scale vehicle, into flight test and make sure that everything that you've predicted through the wind tunnel is confirmed or validated in flight. So the X-48B flew 92 flights. We've now converted into the X-48C, which is our low noise configuration. And it's called the low noise configuration because we have gone from 3 engines to 2 engines. We've extended the aft deck of the aircraft, and that's meant to shield the noise in the downward direction. You'll also notice that on the B aircraft we had winglets that we've now moved inboard to vertical tails, and they shield the noise in the outward direction.
This shielding research could have huge benefits for people who live or work close to airports. If successful, airport noise from aircraft could be reduced to levels that previously would have been unthinkable. In the near future, people who live near airports may not be able to hear any aircraft at all unless they are on a flight themselves. Today's flight test is scheduled to test some new maneuvers to help validate the wind tunnel data. And because the researchers are pushing the envelope of flight with this scale model, no humans are put in danger during the test.
We're an unmanned vehicle. We are remotely piloted, so that means that we do have a pilot that flies it. We have a ground control station that sits in our hangar. The pilot sits in the ground control station along with a flight test engineer, a range safety officer, and a flight director. And so the pilot flies all of the flight cards that we have prepared for him for each of the flights. We test all of our systems on the aircraft to make sure they're working. We make sure all the flight control surfaces are working well, so the pilot who's sitting in the ground control station back at the hangar cycles all of the surfaces to make sure they're working well.
Power's coming in, speed's alive, 10 knots.
Good engines.
20. 30. Tower, Skyrray 48 is airborne, Lakebed 23 right, turn right into the area with chase.
It's about a 30-minute flight that we have on the C configuration. And so because it is piloted, we also have to use the same crew rest rules that a normal flight would use. When the pilot is flying the aircraft, he gets his situational awareness from a camera that's in the nose of the aircraft. So while it looks like there's simulated windows on the nose of the aircraft, there's actually a window that houses a camera that's displayed within the ground control station for the pilot to gain his situational awareness. So he's not just flying by instruments, he's got an out the cockpit view of the flight.
The team prepares for the flight, going through the checklist and making sure that everything is a go. Once all the checks are complete, the X-48C is off for one of its last missions. After landing and with the conclusion of another successful flight, the chase plane performs its traditional barrel roll to show that this flight went perfectly. With the years of data acquired during all the flights of the X-48 aircraft, engineers from NASA and industry will have a much better understanding of the flight characteristics of this non-traditionally shaped aircraft. This data will help them perfect and predict how this type of aircraft will fly when a full-scale model is finally built. As we have shown, NASA uses a building block approach to test concepts for next-generation aircraft. One of the final steps for testing these new concepts comes when hardware can actually be flown on a full-scale vehicle. In this hangar at NASA Dryden, the Environmentally Responsible Aviation Project is taking another step to making flying less noisy and more efficient. For this experiment, the ERA team is repurposing this Gulfstream aircraft to test a revolutionary new concept for flaps, moving from just computer and scale models all the way up to a full-scale model aircraft.
The reason we need a full-scale aircraft is because of the TRL level, the technology readiness level has to go from a 5 to a 6. In order to do that, you have to have a relevant flight environment. A relevant flight environment means you have to have a full-scale aircraft.
With this new craft, the team will soon be changing the existing flaps and moving on to this new technology that has the potential to be a game changer for future aircraft.
The reason we have this airplane is to basically do an experiment with an adaptive trailing edge technology. It's a morphing technology for the trailing edge of a wing. So we have the back end of the wing here, and on it is existing technology that has a rigid structure, this like a flap here, and what it does is during takeoff and landing, the structure comes out and just bends like a board, and you see a separation here that occurs. And what this aircraft is going to do for us now is we're going to develop a technology in flight, demonstrate it, and have this so that it's just, instead of coming out like a board and moving down, it's actually going to morph into a shape that's more uniform and connected. And that makes the aircraft flap much more efficient and less drag. The way we have the test plan now is we're going to have with the flap fastened, we're going to have probably 1 or 2 flights or 3 flights a week over a period of months. What we're going to do is move the flap to a certain position, and then we're going to fly it for a period of time. We're going to map it and take lots of measurements, and then we're going to move the flap a little bit more and then fly it again. So it's actually going to be ground actuated. We'll do this until we capture the full flight envelope.
The material they will be using was designed by a firm called Flexsys. This system uses a highly reliable, elastic, deformable structure to morph from one position to another. This is the world's first functional, seamless, hinge-free wing, whose edges morph on demand to adapt to different flight conditions. The most far-reaching impact of this technology is fuel savings. Studies here at NASA Dryden have shown that even a 1% reduction in drag for the U.S. fleet of wide-body transport aircraft could result in savings of approximately $140 million per year. The Flexsys system has shown even greater potential that could result in hundreds of millions of dollars saved per year. Another huge benefit of this concept is the promise for reducing aircraft noise and weight dramatically. But more testing needs to be done, so the next steps for the NASA researchers is to fly the Flexsys system on the Gulf Stream. The entire aircraft has been stripped down and is now a flying test bed. Generally on these types of research flights, there will be a small crew, 2 pilots up front and several engineers to sit in the back to monitor the data. That same data is also beamed down to the engineers on the ground to validate the wind tunnel and computer models. After all is said and done, this new technology has the potential to be a real game changer in the aeronautics community.
Yeah, this is very exciting technology here because of all the impacts that it has on flight throughout the country and even the world. I mean, the amount of savings this is going to have for fuel is very significant, and not just for the economy, but for the environment. So it's very important that this technology get developed and see to fruition.
As we have seen, there are many ways to test aircraft, from state-of-the-art computer visualization all the way to the well-worn tools from the past. But no matter how it is done, it's comforting to know that every day the engineers of the Environmentally Responsible Aviation Project are continuing to make strides to improve flight for air passengers of today and for generations of future flyers as well.